Section 6.5, Graphing Square Root and Cube Root Functions. The first thing we're going to do is take a look at the parent or base graphs of both of these functions, so you will get in your head what all of these graphs should look like. They will all end up being very similar in their basic shape. And again, if you don't know how to graph something, the fail-safe way to graph anything is to make a t-chart. We should always try to use positive and negative values. But if you notice, you can't take the square root of a negative number. So we're going to disregard those negative numbers. The other numbers that I'm picking for my x coordinates, if you notice, since I'm plugging them into the square root function, I'm picking perfect square numbers. It's going to make it a little bit easier to graph. So the square root of 0, the square root of 1, and the square root of 4. And then if we graph those points, you can see what the general shape of any square root function should look like. Taking a look at the domain, recall, is your x coordinates, and so by either looking at the function or the table of values, or in this case probably the easiest way would be to look at the graph, you can ask yourself how far left does the graph go to how far right, and that will answer the domain question. So this graph can go only as far as 0 to the left. I can't plug negative numbers in. 0 is included, so I'm going to use a square bracket on that side. And it goes forever to the right, so it goes to positive infinity. And again, we use parentheses around infinity because it is such an abstract number. As far as our range, remember our range is our y coordinates. So we're going to ask ourselves, how far down does this graph go to how far up? And again, we can see that it only goes as low as 0, with 0 being included, and it will go up forever. And that's our square root function. Next, we're going to take a look at the cube root function, the parent graph of that. And if we think about a t-chart, remember that a cube root function, we're looking for 3 of the same number that multiply together. So I can, in fact, pick negative numbers for a cube root function. And you'll notice with these values that I'm picking for my x column, they are all perfect cubes. So the square root of negative 8, negative 2, the cube root of negative 8 is negative 2. Of negative 1 is negative 1. 0 gives us 0. 1 gives us a positive 1. And 8 gives us 2. So graphing this as best we can on our coordinate plane, you'll see that this is the general shape of any and all cube root functions. Again, thinking about the domain, we're looking at how far left to how far right does the function go, or what's the smallest number to what's the largest number that I could plug into my x coordinate. And that will take me from negative infinity to positive infinity. This graph will go forever to the left and forever to the right. The range, how far down will the graph go, and how far up will the graph go. And again, it will go down to negative infinity and up to positive infinity. Next, we're going to take a look at what the various numbers, if we multiply or add various numbers in various places, go. And these next 3 examples are going to be dealing with a square root function, but the concepts that we're going to be hitting on will apply whether you're dealing with a square root or a cube root function. So first of all, let's see what happens when we multiply out in front the square root or the cube root by a constant. So again, I can make a t-chart. And again, I have just the square root of x, so I can't pick any negative numbers. But I'm going to still pick those perfect squares. So the square root of 0 is 0, and then times 2 gives us 0. The square root of 1 is 1, but multiplied by 2 gives us 2. And the square root of 4 is 2, times 2 gives us 4. If we graph those points, we'll see that yes, we still have that same basic shape of our parent function. If we compare that to our parent function, we can see that it is stretched a little bit. Taking a look at the domain before we get on to the comparison of these 2 graphs. Again, the domain, how far left does my new function go? Well, again, it still doesn't go any farther left than 0, and it will go on forever to the right to positive infinity. And similarly with the range, it will go down as low as 0 and up as far as positive infinity. So what does that number out in front do? It basically is going to stretch the graph. Each y coordinate is multiplied by 2 from the parent graph. So if you look at your t-charts, your y coordinate has been multiplied by 2. Now let's go ahead and take a look at what happens when we add a number inside the radical. Again, we can make a t-chart. And again, let's see if we can plug in a negative number. And if we plug in negative 1, plus 1 gives us 0. so the square root of that will be 0. The next perfect square number after 0 would be 1. So what can we plug in for x? So we're taking the square root of 1. Well, we can plug in 0. 0 plus 1 is 1. The square root of that is 1. The next perfect number is 4, but we're going to be adding 1. So the number that I'm going to pick for my t-chart will be 3. 3 plus 1 is 4. The square root of that is 2. And the next one I can pick would be 8. 8 plus 1 is 9, and the square root of that is 3. So let's go ahead and graph those values. Again, comparing this to our parent function, what happens when we add a number inside the radical? What happened to that graph? Well, it was shifted to the left. We added 1, and it was shifted to the left. It was shifted to the left 1 unit. So adding a number or subtracting a number inside the radical is going to shift the graph left or right. The domain of my new function, so again, we're looking at how far left does the graph go to how far right. Well, if we look at our new function or our t-chart, we can see that we can start at -1. And again, -1 is included, and it's going to go on forever to the right to positive infinity. Our range, does that mean our range is going to go from -1? Well, no. Our range, again, is still how far down to how far up. The lowest my graph is going to go is from 0, and it will go up to positive infinity. What happens when we add a number outside of the radical? Again, let's make a t-chart. I put in -1 on the last one. Can I plug -1 in on this one? I can't. The square root of -1, because the 3 is being added outside the radical, I still can't take the square root of -1. So again, for my t-chart, I'm going to pick those nice, friendly, perfect square numbers. The square root of 0 is 0. Plus 3, however, gives us 3 for my new y-coordinate. The square root of 1 is 1. Plus 3 gives us 4. And the square root of 4 is 2. Plus 3 gives us 5. So let's graph those new ordered pairs. We can see that our graph is moved up. If we look at our parent graph is basically parallel, but it's a little bit lower. So what does happen when we add a number outside the radical? Take a moment and see if you can answer that. The graph was shifted up. And how many units up was it shifted? It was shifted up 3, that number that's being added outside. And once more, let's take a look at our domain. How far left does this graph go? Again, it starts at 0. How far right? It goes on forever. How far down does this graph go? It starts at 3. 3 is my lowest number for my y-coordinate. And how far up will it go? It's going to go up to infinity. So, what happens when there are numbers added or subtracted inside or outside of the radical? Hopefully you can have seen from those last two examples what they do. And now we're going to be able to use those two shifts to make graphing cube root and square root functions a little bit easier. So the first thing that we're going to do when we graph cube root or square root functions is we're going to find the points on the parent graph. And the parent graph is going to be y equals whatever that number that's being multiplied by, and then the square root or cube root of x. So we're going to disregard what's being added inside and outside of the radical. And then if you can notice from the last two examples, you're going to shift these points h units horizontally, and again we're going to use the opposite sign, and k units vertically. So for example, if this was one of our graphs that we had to graph, the first thing we would do would be to graph y equals 3 times the square root of x. And my t-chart then, I can just get in the habit of using those nice perfect squares, or in the case of a cube root, nice perfect cube root numbers. After I've graphed those points, then I can look and realize that I'm going to shift to the left 2 units and down 5 units. And so then I will graph my new function and connect the dots. Another example, if I have y equals -2 times the cube root of x minus 1 plus 6, my parent function is going to be y equals -2 times the cube root of x. And I'm going to make a t-chart with perfect cubes. And then I can shift that right 1 unit and up 6 units. So now let's take a look at some of these problems. My parent function is going to be y equals the square root 2 times the square root of x. Making my t-chart, picking the numbers for my x-coordinate should be fairly easy. They're just going to be perfect square numbers, and I just need to take the square root of them and multiply them by 2. I'm going to plot those points, but we don't need to connect the dots because that's not actually our function. We're then going to realize that we're going to shift each of those points left 1 and up 3. So each of those points, we're going to go left 1 and up 3. And after I do that, I can connect my dots. Determining my domain, I can't really use my t-chart because my t-chart dealt with the parent graph. I could possibly use my equation and I could look at my graph. So how far left does this go? It starts at -1 and goes forever to the right. For the range, how far down does it go? It starts at +3 and goes up to infinity. Let's take a look at one more example. This is a cube root function. So again, my parent function is going to be y equals the cube root of x. My t-chart is going to include the perfect cubes, both positive and negative. And I'm going to plot those points but not connect the dots. Then I'm going to realize that this means that I'm going to shift each of those points right 4 units and up 2 units. So when I do that for each of these points, I can connect those and have my cube root function. The domain, again, cube root functions are going to be -infinity to +infinity. They'll go on forever to the left and ever to the right. They'll also go forever down and forever up. One thing that you might be asked on a cube root function is to find the turning point. And the turning point is going to be this middle point. The middle of these 3 that appear to be right in line. So this turning point is going to be 4, 2. It's a similar point as the starting point of a square root function. Do you have any questions? Please make sure if you have any questions you bring them to class. I'd like you to take a look and think about what else have we graphed that's had a similar shift of h and k. There's actually been 2 things that we've graphed. Actually, you graphed them in the first half of this class. So if you want to come in and be the first to tell me, we'll see what can happen. And we'll see you tomorrow in class.